Okay, the main tool in dealing with models that can be given by single equations is the so-called phase line analysis. This is such a handy tool and it's so easy. It probably deserves a lecture on its own. Just to make it clear, this applies to what we call autonomous ODEs, meaning that the right-hand side depends only on the dependent variable, unlike some right-hand side that depends on t only. So just to make it clear, if you have an equation, let's say y prime equals t minus y, that's not autonomous. So the right-hand side of the ODE must depend on the dependent variable only for this tool to work. If you have an autonomous equation, as you should know already from the notes, some of these equations, not all of them, but many of these equations have what we call equilibria or equilibrium solutions, which are nothing but constant solutions. So out of many solutions that the differential equation has, some of them are in the form of a constant. So to give you an example, if you have an equation, let's say y prime equals 2 minus y, y minus 1, y, let's say, plus 2. If you actually run this equation in a plotter, and maybe you should just do it to see how it looks like, you will notice lots of curves. But all these curves, you will notice 3 straight line solutions. So 3 horizontal lines corresponding to the constant solutions. Because remember, if your ODE has a constant solution, so if you have basically, if you could replace y of t with some constant to make it a solution of the ODE, then the left-hand side becomes 0. And then you won't have to actually guess to see if you have a constant solution. You just basically set the right-hand side equal to 0. So in a nutshell, basically to find constant solution of equilibria entails to set the right-hand side of the ODE equal to 0. If by setting the right-hand side equal to 0, you get constant values for y, those are by definition equilibrium solutions. Y 0, again, because the derivative will be 0 if you have such a solution. Not all equations have constant solutions, but those that do have them can be found by setting the right-hand side equal to 0. So obviously here you will have basically 3 constant solutions, 2, 1, and minus 2. And in the plotter, if you sketch y with respect to t, out of the many curves you will see when you click on various solutions, you will see basically 3 straight lines at minus 2, at 1, and at 2. Those are important in modeling work because, for example, if your solution converges to one of these constant solutions, then you have basically predictive power in the model, because you could say in the long run, the solution approaches that number. This is the so-called stability question, meaning that an equilibrium is stable if nearby solutions converge to it. There are more precise definitions of stability and what constitutes a point unstable. We'll get into that if necessary later. But for our purposes, basically, if you have initial conditions in some neighborhood of the equilibrium point or the constant solution, do those solutions, the nearby solutions that start nearby, converge to that or not? So the beauty of this phase line analysis that I'll talk about right now is that one can answer this question for single ODEs just based on the sign of the derivative. Again, one needs an autonomous ODE, so you need the derivative to depend just on the population size, to use the language of math biology, not on the time t. And while there is actually a proof for what I'm going to talk about right now, we're not going to go over the theory behind it. We're going to just basically go on the intuitive aspect of it. So imagine that instead of actually sketching the full solution with respect to t, I'm just looking at how the y values change. So that's why I like to do the phase line analysis based, looking at the vertical line. In some books, they do this with horizontal lines. It doesn't matter. Just imagine that I'm looking just at the y-axis when you sketch y with respect to t. So I don't care about the value of t. I only care about how the values of y change. And start by placing the equilibrium values in the correct order. We have 1 here. I should put maybe the other one a little bit further down here because it's anyway, it doesn't matter. Let's just label it. The most important thing is the label, obviously, and put them in the correct order. You don't have to count the units here. So let's say this is 1 and this is 2 and this is -2. And now imagine that you basically start with an initial value of 0.4 y at any of these parts of the y-axis. So starting with the portion above 2. And you could actually plug in an actual value above 2 just to make it clear. Let's say you plug in 3 into the ODE. So let's say you start with y naught equals 3. Now if I plug in 3 on the right-hand side of the derivative, and you could do this mentally quickly, you don't have to do it explicitly like this. The sign of the derivative in that case is, what is it? Let's see, it's negative, positive, positive. So that's going to be negative. You don't even have to compute the value. You just have to find the sign. And again, you could do it mentally, all right? So any number greater than 3, 5, 3, excuse me, any number greater than 2, 3, 5, 4, whatever, will make this parenthesis negative, positive, positive. So because y prime is negative, whenever you plug in something above 2, that means y decreases. And so you indicate this with an arrow pointing downward. Let me erase this part here because that may be misleading. So if you start above 2, the arrow points downward. And then between 1 and 2, again, you can plug in a test value. Let's say you plug in 1.5, and then that makes it positive, positive, positive again. So if I plug in 1.5, I get 2 minus 1.5, 3 minus 1.5, 3 plus 1.5. Obviously, it's a positive number. So if you start between 1 and 2, the solution approaches 2. And let's say you start between -2 and 1. You can plug in 0 if you want. That makes it negative, so the solution goes downward. And again, if you start below -2, again, you can plug in a test value and the solution goes upward. So it's nothing but the sign change of y prime. But you indicate with arrows whether y decreases or increases, right? So assuming that y increases upward and decreases downward. So notice that the stability in this context means that if you start close to 2, not too far from 2, right? So I mean like in some regions around 2, the solution approaches 2. Once the solution approaches 2, of course, the dynamic stops because y prime approaching 0 means that at that point, the solution neither increases nor decreases. So for that reason, this point is stable and this point is stable. I should call them locally stable because again, it doesn't mean that no matter where you start, you approach 2 or -2. You got to start in some sort of region around 2 to approach 2, and you need to start in some region around -2 to approach -2. And of course, it seems that the solution moves away from 1 if you start close to 1, which is the reason we call this point unstable. So this is a textbook example. We're going to move to the previous example right away, the one with k over mu. I just want to emphasize again that all you do with the phase line analysis is a sign table of the right-hand side of the ODE. The right-hand side meaning the derivative of the ODE, after you find the equilibrium points, if any. And believe it or not, with just this simple tool, you basically can answer modeling questions of various kinds. In this case, for example, we could answer by saying if you start with initial condition above 1, so if y of 0 is greater than 1, then y of t approaches 2. Now, don't get used to long results like this, because again, in real life models, most of the time it's not that easy to be that precise. I mean, sometimes you can just say the limit, but you can't be that precise in terms of the condition that you have to impose to begin with to approach that limit. But this is essentially most of the time as good as it gets. And it's actually pretty good if you think about, because you predict essentially what happens in the future, right? I mean, I know it sounds kind of too much to say, but at least in the context of a basic equation, it is as good as it gets, which is the reason why single equations models are the best you can get in terms of model predictions. Unfortunately, of course, realistic models rarely, if almost never, can be described by single differential equations. Okay, let me get back to the problem with k over mu, just to see how easy it is to answer those modeling questions just by doing the phase line analysis. So remember the ODE, that population model, was dPdt equals k minus p over, minus mu times p. K was the recruitment rate, and mu was the death rate. So let's say I don't care about the solution at time t, I only care about the limiting behavior of the model. I set the right-hand side equal to 0, and I find one equilibrium point. So k equals mu times p, right? If you move mu p to the right-hand side, p is k over mu. It is important to actually make some sort of notation that distinguishes the equilibrium value from p of t, because remember, p stands for p of t. K over mu, you can just call it p. This is not a function of t. This is a constant, right? It's a constant solution out of many possible solutions of the ODE. So it's important to denote it by p star. Sometimes if you have more than equilibrium points, p1, p2, etc. But call it p. That's important because it has to be related to p of t. But put some accent to it. Other common habits is to make it a hat or a bar on the top, some sort of accent that makes it clear that this is not a function of t, but just a constant solution or an equilibrium point. The phase line analysis basically entails only one possible sign change around the equilibrium point k over mu. There's only one equilibrium point, and this is the axis for p of t. What is the sign of p prime of t, depending on whether you start above or below p of this p star, of this equilibrium point. Now, one of the challenge here is that you don't actually have test values in terms of numbers, because again, everything is in terms of letters here, right? If it helps, you can actually plug in actual numbers, but you should kind of learn to deal with parameters straight away. So what happens if I start with some population above k over mu? Okay, what is the sign of this expression if p is greater than k over mu? Well, you can just basically rewrite the inequality in the terms you have here, right? I mean, if p is greater than k over mu, well, that's the same thing as p mu greater than k. And then if you move p mu to the right-hand side, that's k minus mu p less than 0. So this quantity, and you have to be careful here not to mess up this inequality, right? I mean, to keep the order of the terms in the correct way. But obviously, if you start above k over mu, then k minus mu p is negative, and therefore p prime is negative, so therefore p of t decreases. And below, of course, there's a sign change. I mean, if this is reversed, so if you start with a value less than k over mu, then of course rewriting this inequality leads to 0 less than k minus mu p, which means k minus mu p is positive, so therefore it increases below it. So you have a single equilibrium point that it's stable, right? Just a single equilibrium point, and it seems that no matter where you start, you approach the equilibrium point. So it means that the limit of p of t is k over mu, and if p naught is less than k over mu, so if you start here, then p of t increases. If p naught is, oops, it's out of range, sorry about that. If p naught is greater than k over mu, p of t decreases. All of this just based on the phase line analysis. Unless the homework explicitly requires the explicit solution of the ODE, don't solve it. So let me actually write it down to make it clear, because sometimes this is a confusion. Unless, sorry about that. So unless asked, do not solve the ODE. So do not solve the model, just use stability analysis. There will be another context in which we actually solve the ODE, but we'll get to that later. Apart from those two cases, we don't actually solve the ODE explicitly. So there will be one more part in which I want to comment on the meaning. That's another very important part of the, so don't rush it, of this first lecture. The meaning of the 1 over mu, or in general, what we talk about, what we mean by removal rate from an equation. So stay tuned for the last part.